Hello, everybody. I'd like to welcome Yota Toyama, who's going to tell us a little bit about a small implementation of R7RS scheme.
Thanks so much for your introduction. I'm Yota, and I'm a developer of Stak Scheme. And in this talk, I'm gonna introduce a new tiny R7RS-small Scheme implementation called Stak Scheme. So as a background, there is a R4RS scheme implementation called Rivet Scheme. I think there was a talk in this workshop a few years ago. And it's a really small R4RS implementation. As it's level was only 7 kilobytes in binary. Then something interesting about Ruby scheme is that its virtual machine aims to be compact, portable, fast, and simple at the same time. And Ruby scheme is composed of two components. One is a bytecode compiler from scheme source code to bytecode, and then they implemented their virtual machines in many languages, proving portability, including assembly, C, JavaScript, Bash. Yeah, that's really interesting. So I was really interested in this project, and so the question is, can we implement the entire R7RS-small standard on this virtual machine of Rivet scheme, RVM? The answer is yes, we did. Yes, we did. So that's how the project of Stak Scheme started, and it's a R7RS small implementation, so it's quite bigger than a Rivet scheme. But it still aims for the same language design of Rivet scheme, compact and portable. And there are two use cases for this, and one is running it inside some other host programming languages environment as a scripting language. Other use case is that you run it as a standalone interpreter, and it's open source on GitHub. And in terms of the differences between the Stak scheme and the Rivet scheme, they are a bytecode and decoding is quite different, and also the implementation of the eval procedure is also debated quite a bit. So I'm gonna talk about those two topics today. So before going into the details of the Stak scheme, I'm gonna explain the Rivet virtual machine. So Rivet virtual machine is very basic Stak machine. But something interesting about that is that everything on the virtual machine is actually represented as lists. So that includes code, bytecode, and also runtime values in scheme, and virtual machine states are also lists. For example, call stacks or value stacks to calculate something. So this is a Rivet virtual machine implements adapts a polynomial architecture, because you can manipulate code and data on the heap memory in exactly the same way. And the right side is examples of the data structures on RVM, and the upper is string. The root a pair is just a pair of lengths of the string, and the pointer to the list of characters, and in the list of characters, like it just stores the code point. And yeah, like this is so on the like RVM representation of like scheme program is called like a code graph, and it's actually just like a DAG of like pairs. And as I mentioned, like it contains both code and data in exactly the like a same structure. And yeah, this contributes to like a simple implementation of the eval procedure, but I'm gonna talk about it more later. So like RVM or like a Ruby scheme or Stak scheme consists of like two components. Like one is like a compiler and the other one is virtual machine. And yeah, like compiler is just like a compiler of text of like a scheme program to the like a byte sequence. It's something like a bytecode. And the virtual machine like takes like a byte sequence of like scheme program and then executes it. Like the point is that like inside the compiler and inside the virtual machine in both components we use like code graph as like intermediate representation of the scheme program. So in the compiler, like we compile the text into a code graph or memory, and then like later like we encode it into a byte sequence. Like on the virtual machine, like, we do the opposite thing. We first like decode the like byte sequence into code graph, then execute it. So let's take a look at the like one of the example of the code graph. So this is an example of R7RS-small standard. So it doesn't work on Ruby scheme. But, the upper is the library definitions and the lower is main program. And in the like, library, we define a symbol called foo, and then like in the main program, we import like with some prefix, and then we define another like a foo symbol, and then like use it in the like final like, expression. And when you compile this into a code graph, it would like yeah, like how do we encode this code graph and how it's different from the like Ruby scheme. So in contrast to like a Ruby scheme, like a Stak schemes, like code graph encoding is more close to like conceptually more close to like a structured memory snapshot. So you can basically like transfer the exact like memory heap memory state inside compiler into the virtual machine. To do that, like, if the like a code graph is like basic like tree, you can use some like a DFS or something to like do a topological sort, but there are some like merges like those symbols, right? So for those to encode those shared nodes, like we like simply like cache those shared like on during decoding, and yeah, like but like we want to make the like decoding algorithm portable. Like for example, like we implemented the virtual machine in Rust, but at the same time, like we want to also target, for example, embedded devices. So we don't want to use some like a complex data structure from the host language. So this cache table is actually implemented as a list on the like, heap memory of the virtual machine. Like this is the story. This is the kind of trick to keep the like decoding and encoding algorithms portable and also like simple. So by having this like a memory snapshot algorithm, like what we can do is like we can naturally encode like those like shared nodes which appear in the code graph. For example, like sometimes if instructions have like a continuation for both like them and else bodies, these are like encoded as shared nodes, and also like we can encode like symbols from different libraries without any manipulation of the code graph or like a pre-processing of the like a code graph. Yeah, another thing is that how we implement like eval procedure. So in Stak Scheme, like in Revit Scheme, the compiler is actually like a separate library. So when you want to like use like eval like a library, you need eval procedure. You need to attach that into the like a main program and then compile it. Like when we do that, like in R7RS small implementation, it's gonna be really tedious because we want to also we need to like maintain both like a macro and library systems in those two like separate implementations of like compilers. And so instead, what we do in Stak Scheme is that like we use like we reuse like a part of the compiler as a like component of like the eval procedure. So what we do is first extract like a compiler of S expression to the like a code graph as a data, like this variable. And then there is a like an incept function in the compiler, and then like it intakes the compiler data and source code, and then it embeds the compiler into the source code. And then when you evaluate like a compiler variable, you get like a compiler function from the expression to the code graph. And yeah, and then like when you apply the like a compiler function to the source code, you get the final code graph. And then you can like encode the code graph, and then you finally get like a byte sequence, something like a bytecode. And it's like we have two like big features. One is like a hygienic macro system, and another one is like a library system. So like if you like if you remove the eval procedure from the like standard, you can actually like expand macros and libraries completely at like statically compile them. But the eval procedure actually needs those information at runtime. So for example, like macro definitions or like, initialization code for libraries, and also like what like symbols are exported from each libraries. So to encode and decode like this information, we like we basically exploit like like power of the like a memory snapshot algorithm I just described. So like those states are like represented as another like a DAG of the pairs and then embedded into the photograph, and then after that the memory snapshot algorithm automatically encodes and decodes like those compiler state, and then we can extract the restore the compiler state at runtime in the scheme eval library. So we evaluated a Stak Scheme in two ways. One is compactness, and also another one is computation time. In terms of the compactness, we compare the lines of code and also the binary size of the interpreter. And for reference, we compare the TR7, which is the tiniest R7RS-small implementation before Stak Scheme. And in lines of code, we almost halved the number of lines. And in the binary size, we have almost 3 times more binary size of the interpreter. This is mainly because we implemented most of the logic for those rebel interpreter in Scheme itself. Those are represented in the serialized code graph. It's by sequence. So that's why it's so small. TR7 is mostly implemented in C, so that's the biggest difference. So in terms of the computation time, this is a relative computation time of different benchmarks. When you look at the last 3 rows, they are computation heavy benchmarks. When you look at the result, Stak Scheme is pretty much comparable with existing traditional implementation of the scheme R7RS-small scheme interpreter, including the TR7. But at the same time, compared to the most modern interpreter Gauche, it's still far behind for performance. When you look at the top 2 rows, they are benchmarks of just executing an empty scheme program, and the other one is a hello world program. I added those to evaluate the startup time latency of those interpreters. And when you look at middle 2 parameters, marked embedded, they are benchmarks of executing just bytecodes, which is embedded into the host language, in this case a Rust programming language. So in those cases, we have a really small such startup time latency, even compared to the very modern implementation of the interpreter. So this means that the architecture of the Ruby scheme or Stak scheme is very suitable for those use cases of the embedded scripting language. And in terms of the future work, so I said that RVM aims to be a compact, simple, fast, and also portable. But what it lacks is security. This is because the nature of the kind of for normal architecture of the Ruby scheme. for example, like you can directly modify the like state of the like a stack using the like very primitive procedures in like Stak Scheme. To prevent this, like we are planning to add like a type checking for for those like very primitive procedures. And another thing is that like we implemented like virtual machine only in Rust for now, but to prove the actually prove the portability, we are planning to like port the virtual machine into other host languages, like including Go. Um, yeah, there are some other like small discrepancies between the full implementation of the like R7RS standard. For example, it doesn't have like a Stak Scheme doesn't have like a full numeric tower yet, and also it doesn't like implement the it implements like a Unicode I/O, but it doesn't fully support like Unicode case conversions in like a scheme character library. That's basically all. Yeah, thank you so much for yeah, developers of the like a release scheme and also like early like reviewers, including William. Thank you so much for listening.